Okay, so now I'm gonna jump into the substance of this tutorial, my part in the tutorial, which is about algorithms for discovering discrimination. Like how can we discover that an algorithm or a group is discriminating? We're going to have some definitions, and then I'm going to speak about the data mining approach. That's again the substance of the tutorial, of this part of the tutorial. And then very briefly, I'm going to mention close to the end some case studies and something about the web as an environment where you can also do discrimination research. So this is the discrimination discovery task. This is the kind of a very broad problem formulation. You are given a database, and this database contains decision records. So this person got the loan, didn't get the loan, and then all the attributes about this person. Sometimes you get a subset of attributes, and you want to find discriminatory situations, and you want to find discriminatory practices in this database. Right? This is the task. In the input you have the outcome, which is whether this person was hired or not. So let me unpack this a bit more. So the input, you can say, well, you have these decision records. You have to know what is the criterion for unlawful discrimination. So you have to know as an input, you are told under this, in this country or in this legislation, you cannot discriminate against for gender or nationality, and you are allowed to discriminate about these other things. Fine. This is input to the problem, to the system or to the algorithm. And the third thing is, of course, what are these specific groups that you care about, right? So you can say you cannot discriminate by gender, particularly you are not allowed to pay a lower salary or offer a lower salary for people just for being female, okay, for being women. And the output you're supposed to generate in this discrimination discovery is a subset of rows, and these rows should correspond to certain number of decisions that affect a specific group or a set of groups. So your output should be these rows, and then some extra information saying I'm actually selecting these rows because these rows correspond to whatever people of Hispanic origin that got a lower salary. Now, why is this task? Why do we even do research on this, or are we inviting you to do research on this? Is that there are many different concepts about discrimination, all the ones that I mentioned in the first part and more. There are many contexts and many scenarios in which discrimination can happen, and perhaps a problem that appears over and over is the fact that either you have incomplete data, so you don't have the person claims that they didn't use a certain attribute, and actually they don't even show you that they have this attribute, and the data may have even been pre-processed, and you don't even you have only like some aggregates or some very generic information. I'm going to show you some methods that actually can go can work even in these difficult kind of cases. And now, just as researchers in networks have the Sakari's Karate Club, if you have worked on that, like it's a small network that has been studied over and over and over and over. So you know a lot of properties about this network. There is this German credit score data set that has been used, is basically used as a kind of a test bed for many researchers that do, for a lot of research that does non-discrimination. It contains 1,000 people. And for these 1,000 people, they have, I don't know, a couple dozen of attributes about whether this person was employed, was married, was single, was male and female, whatever. You have all these attributes about the person, whether this person, how many years have this person lived in Germany, and so on. And then you have an outcome, which is whether this person has good credit or bad credit for the bank. And this good credit and bad credit actually reflects in whether this person got a loan or didn't got a loan in the end. So it's a small data set, and it's used over and over, like for doing small tests and proof of concepts, and then there are larger data sets that are used for more detailed analysis. Now, we're in a data mining conference, and I have to say that the data mining provides this great tool for discovering discrimination, interested in data mining can also actually help to discriminate people more, but you can actually use the same tool for good to try to discover that in a certain record of historical decisions, you actually, there was some discrimination going on. I'm going to speak about 6 different kind of approaches to discovering discrimination. After the break, my colleague Francesco will speak about how to mitigate and reduce discrimination. I'm going to focus on how to discover it. And these approaches include like doing some meta mining. You create classification rules, and now you mine these classification rules to find out group discrimination. There is an approach that uses KNearest Neighbors and is mostly about individual discrimination. An approach on Bayesian Network, an approach that exploits probabilistic causation. Some approaches related to this privacy connection that I was speaking about, and some approaches related to predictability that can also be traced somehow back to privacy. So let me start with classification rule mining, which is based on a series of papers involving Dino Pedresci and associates in KDD, from KDD 2008 to 2010, and even now they continue working on this topic, and it's about doing some mining on the classification rules. So what they need to work, when these approaches need to work, is a definition of what are these potentially discriminated groups. And these potentially discriminated groups are specific attribute values that are protected, right? So in this case, you need to give this as an input. You need to say, well, there is a group which is people older than 50 that somehow has been codified in the legislation or in some regulation that you cannot discriminate against. Or there is a group that are people with disabilities that you cannot discriminate against, or you cannot discriminate against people by their sexual orientation, but you have to say, for this approach to work, you have to say what is the sexual orientation that you care about, like what is the protected group that you care about. Like this is again, come back to this idea that this is trying to create a balance, not to preserve one, to create a balance. Now, given that discrimination can be the result of several characteristics that happen at the same time, because these things depend on each other and they have consequences, and maybe because you were in a certain group, you had less opportunities at a certain point, and then there are many consequences that are also other attributes in the same input. We're gonna these approaches that are based on mining classification rules speak a lot about item sets. Okay, and this is gonna come over and over. Now, if you know, these association rules are this kind of if-then statement that say, okay, if you have certain attributes, then you have certain consequences. Typically, the X is going to be everything I know about a person, and the Y is going to be whether, the consequences, whether this person got a credit or didn't get a credit, got a job or didn't get a job, and so on. Now, let's speak about, so this approach works as follows. You take your database and then you mine this database for this database of historical decisions. So there is a column, it's going to be column C, and this column C encodes, or it may be a set of columns, but they encode the outcome, right? The income, the salary, the height in decision, and so on, right? And we're going to mine this, use a standard. We're going to assume that as a black box, we use some classification, some rule mining algorithms such as association rules. We extract these rules from the data set, and now you're looking at the rules. And with these rules, you're supposed to do something. You're supposed to discover whether people were discriminated or not on the rules that you discover on this database that has been augmented with the decision column or columns, right? Now, of course, the most obvious thing you can look for it, you can look in this data set, is that I want to look for association rules where on the left side I have a protected attribute such as gender, and if I found like a gender, let's say female gender implies no higher, if I find this rule with high confidence in the data set, then I can immediately stop the algorithm and say, here I have evidence of discrimination in this data set, right? Usually it doesn't happen, that it's not that easy. You find lots of rules and then you look for direct discrimination, which are rules in which on the left side you have some potentially discriminated group and some protected group, and some B which can be a context. So this can be some AB implies C, can be something like, let's say whatever, black people living in New York are given a a prison sentence, and B is like the context, which is something that you are allowed to use, and A is something that you're not allowed to use, such as race, age, ethnicity, whatever, depending on the specific application. Now, of course, you can actually find, if you are interested in finding discrimination cases, you can actually find the opposite. You can find in this database of rules that favor a certain group. If you find something like with high confidence, people who are male and have no history of saving money but get a credit with high confidence, then you can claim, well, there is favoritism. They are being favored by whatever decision process is taking this, algorithmic or human. Now, it gets more complicated when you enter this area of indirect discrimination. So, because now you don't have in the rule the gender, for instance. You don't have a rule as obvious as saying if you're female, then you don't get the credit, right? You have other attributes. So, for instance, you have a rule such as that one. If your zip code is 10451 and you live in New York City, then you don't get a credit, right? You find this rule by mining your data set of decisions. So the people who didn't get a credit can be are very easy to explain by this rule. And now you need background information in order to claim or try to claim that this rule is discriminatory or that it uncovers discrimination in the data set. You need background information, right? So let me show you an example of that. So suppose we look at the data set augmented with this column that has the benefit, like whether the people got the benefit or not, and you find this high confidence rule A that says if the neighborhood is 10451, then do not give the benefit, or do not give the credit, do not give the scholarship, and so on. But suppose you also know with high confidence that in this neighborhood there is a predominantly black population. Then you can derive a new rule that says, okay, if you have black people in this neighborhood, then deny the benefit. And if you have high confidence in rule C, then you can tell that rule A is indirectly discriminating against blacks. Of course, this is all qualified by how confident, what's the confidence that you have in all these specific rules. Now, this requires a quantification. And this quantification is going to come from some of the measures that we described before for discrimination. And it's going to, in this case, this quantification is going to come from something that's called the extended lift. That it's a concept that is going to appear more in other techniques for measuring discrimination. So the extended lift is basically the confidence of the rule AB implies C divided by the confidence of the rule B implies C. So think of A as something like, for instance, think of A as gender female. So A is being a female, and B is living in San Francisco, and C is getting a loan or a mortgage denied, right? So you want to look at, okay, if to what extent, and you know that let's say confidence B to C, the denominator tells you how many people living in San Francisco that go to try to get this mortgage don't get the mortgage, right? This is kind of your baseline, and now you're comparing that against what are the proportion of people that are female and live in San Francisco that don't get the mortgage. And if this ratio is very high, then you can claim that females are being discriminated against, right? So you have this, you're trying to look for these rules where you have a lift an increase in the confidence that is explainable only by these protected attributes that you were not supposed to be using in the first place. Okay? And there is this, the authors in these papers about non-discrimination, they define the concept of alpha protection, and they say your database is alpha protected if anytime I find a rule that has this property that if you add a protected attribute, my confidence in your decision increases. If every time I find this, the increase is not so big, then you're fine. Your outcomes can be claimed to be alpha protected. But if I find one rule where where I can show that by augmenting the data with this protected attribute, I get a big increase in the confidence of the negative outcome that you are giving to the people, then I can claim that you're alpha discriminatory, right? So alpha is this threshold for discrimination. Think of something like 3 or 4 or something like that, right? So you're affecting people, you're affecting some group 3 times as more as the baseline that you observe for the people who have the same context, right? Now this is related to group representation. It's just a matter of algebraic manipulation. So the extended leaf in some way is the ratio between the proportion of people in the protected group A in the context B for the outcome C over the OR proportion of these people in the group. Like think of, okay, how many females live in San Francisco and how many females live in San Francisco who don't get the credit, right? And then this is kind of another way of expressing basically the same idea of the extended lift. And remember, there is a parameter that is going to be given that's going to tell you up to which point you are allowed to do this and at which point you are not allowed to do this, which is going to be the alpha protection. So suppose you have alpha equal to 3. Let me give you an example of direct discrimination. You have an element, like you add the race, and then you increase your lift by 3 times, of course. Let me give you some other example of in the German credit data set. So for instance, look at rule B. Rule B is a very innocent rule, right? So rule B tells you, well, you didn't have any savings, so we didn't give you the credit. And this explains like a big chunk of the people who got their credit denied. It's fine. But now you look at rule A that looks at people who are female and are divorced or separated or married, and they have the same status and they don't get the credit, and there is an increase. Now, in this case, the increase is not so much. So if alpha was 3, we will say this is alpha protected. Now, let's look at another example. And here we're going to add 2 attributes. Notice that first you have rule B, which is innocent. And it says like if you want a credit to buy a used car, for some reason, the bank has decided that you're probably not going to pay so much if you're asking for a credit to buy a used car. So they are with some. This explains some chunk of some piece of the credit denies. But if now I add that this person is female that was divorced, separated, or married, and is older than 52, and now I have a 100% confidence in this rule, and I have increased it like several times my confidence, more than 6 times, and then we will claim this rule is alpha discriminatory. So we have found some reason to believe that this German credit agency is discriminated against this particular group that has these 2 attributes. Actually, there are some experiments in the paper where they change the threshold and they change like the minimum support that you require. So for instance, you have here like alpha equal to 2. This is not bad. And on the left side, you see for alpha equal to 2, you find some rules like a few tens of rules that are alpha discriminatory that have a minimum support of 1% over the data. So they affect like several cases. And of course, the higher you put the threshold, the less discrimination you're going to find in your data set, right? Obviously, if you the higher alpha corresponds to cases where you're really kind of brutally discriminating against a certain group. Now, notice that in some cases, notice that initially you have these 2 sets of attributes, right? Protected and unprotected. Protected are being female, being black, being Hispanic or whatever, being old, and then unprotected are all the other things. And there is among the unprotected attributes, there is a particular class of attributes which are these genuine occupational requirements, or genuine or whatever. These are the things that you can legally use for deciding whether to give the job or not, such as having a driver license if the job involves driving. Right? So you try to find, you have these kind of candidate rules, and at some point you need to check your candidate rules against these occupational requirements that are okay to use, right? So let me give you an example. Suppose by some by some reason in some country females are not allowed to drive, so no female has a driver license, then you look at the hiring decisions for a job that involves driving, and then you can claim as the regulation authority that actually this was based on an occupational requirement that was having a driver license, right? Of course, things are never, not all the world is Saudi Arabia. You have other places, and in these other places you may have a different situation. So for instance, think of a classification rule such as this one, right? So you find with confidence 0.58 that if you're a female living in New York, then you were not hired for this job. And now suppose you find in rule B that actually if you didn't have a truck driving license, that you were not hired with another confidence. So suppose this is a job that does not actually require you to have a driver license, but for which having a driver license is really, really important. If you don't have a driver license, you really have to have many other qualities for us to hire you, okay? So you have a truck driver license, this is kind of a soft requirement, but there is a strong requirement anyway. It's soft, but it's high, okay? So it's okay that the company wants to prefer people that have this truck driver license, but the company can also choose to hire other people that don't have the license because for some reason, right? And now suppose you have with high confidence that female living in New York do not have a driver license for driving trucks. And here they propose this P instance of a protection and of a potential and non-discrimination rule, and they say, well, if you have a legitimate ground for the decision, and if you have that the confidence of the rule involving these legitimate grounds is more than P times the confidence of the rule that doesn't involve it, then this is a P instance of a potential and non-discriminatory rule, and you can actually claim, I mean, what the authors claim here is that if you find such cases with a large P, then you can say, well, I cannot claim that this was really discriminating against female. It was discriminating against people that didn't have a driver's license for trucks, and it happens that those are females too. In this case, for instance, if you do the difference, like you can say that this is 0.9 P, it's a 0.9 P instance of rule B, which means that with this parameter 0.9, you can use this to claim that this discrimination was not against women, was against people that didn't have a driver's license to drive a truck. These authors in their work, they also propose a pipeline, a series of steps. They say, okay, you use your classification rule mining as a black box, and then you obtain these rules that are frequent, and then you use some way of reasoning about these rules. And remember that these rules that you have extracted them from a data set that is augmented with the decision column. And the rules that you care about are mostly the rules that involve this extra column, the column about the decision, right? So those are the ones that you're going to claim in the end are discriminating or not. And they actually say, well, you can actually use a similar pipeline to mitigate discrimination. There are ways in which you can come back to the data, come back to the algorithm and so on, and change the way things work in such a way that in the end you will have an empty set of discriminatory patterns, for instance. Okay, let me move on to another set of methods which are based on KNearest Neighbors. Remember that the classification rule approach is based on discovering that a group is being discriminated. Now, this KNearest Neighbors approach is based on trying to find out whether individuals were discriminated. And it's going to look at consistency, right? Notice that the classification rules approach has some problems. So first, it is problem about like whether we are comparing people that have the same characteristics or not, right? So maybe in certain cases, having a certain race means that have an impact on other characteristics, and then in the end, even if you remove the attributes of being a man or a woman or being of a certain race, you still have some difference, and some of those differences may even be occupational requirements, and it's fine for you to decide to choose on those, whether to hire people or not, or those differences may be your ability to pay a credit, and maybe it's fine that you use those. So in the classification rule, you're kind of comparing, sometimes you're comparing apples to oranges. So you're going to look at things that are more, that people that differ on these legally allowed attributes, right? There are also some problems about the interpretation. There are some issues, some technical issues. So let's look at something that is quite old, that is called situational testing. So situational testing is an investigatory tool, like a tool for lawyers to, or for prosecutions to try to find out if someone was discriminating, and it basically is an A/B test for whatever thing, right? So you send two people, a man and a woman that have identical skills, you send them to apply for a job, and if one of the two gets the job and the other doesn't, and they were identical, then you say, well, I have tested this situation, and I have seen that these two people who were equal in every aspect except that one was a man, the other was a woman, the woman was discriminated, and this is happening over and over again, right? So the idea is to find these pairs of people that, of course, they are not going to be identical, but they are going to be very similar in certain attributes, right? So this is the kind of the idea, and this idea is pre-existing. Now, what is new in this paper is that they say, well, let's use this idea of situational testing, let's use KNearest Neighbors, and let's find out whether individuals are being discriminated or not. How do we do it? Okay, first you need the decision, which is going to be this column that tells you whether you were denied a benefit or granted a benefit, or what was the salary that you were offered in the end, and so on. PR are going to be all the protected columns, the protected attributes, attribute values, suppose women. And UR is going to be the rest of the data that are people who cannot claim that they are being discriminated because they are a majority, and so on. So instead of having pure situational testing where you have these people who are identical except that they differ in the protected attribute, you're going to have people who are very, very similar, right? So you're going to define this distance. And what's important is that this distance function, you have to define it over the non-protected attributes, right? So these people are similar in everything that is relevant and is legally, and you are legally allowed to claim that they are similar, right? So you remove the attribute gender, you remove the attribute race, you remove the attribute age, you remove all the reasons that you are not allowed to use for discriminated, and over the rest of the attributes, you compute the distance, okay? And now you're looking at pairs of people who have a small distance. Actually, you're looking at a neighborhood. And this is the algorithm. It's very simple. You look at the k closest neighbors in the protected set. So in this case, this point R is a woman, and she didn't get the job. That's why it's in red. And you have on the left the k nearest neighbors that are in the protected class. So the k women that were very similar to this R who applied for this job. And you also have the K and N U, which are the four, in this case K was 4, the 4 men that were the most similar to this point R. And now you look at the proportions of people that didn't get the job, right, in the group of the protected neighbors and the group of the unprotected neighbors, which are female and male in this case. And you compute the difference, right? So you're looking at whether you have a difference that is very big around this person R with respect to the proportions of people who got the job and didn't get the job, right? In this case, and this is the basic idea, right? So K is expressed like as a percentage points of difference or some other. You can think of K as the difference as expressed like in some percentage points, and K is a usually small number. So, for instance, let's look at some results. These are in the German credit data set, and they are using K equals 16. So you take a person in the data set, you take the 16 closest persons who have this attribute value and the ones that don't have it. So for instance, let's look at we're going to say, we're going to test 3 cases like young people, old people, and people in the middle, right? Young is going to be 25, old is going to be 60, and now you look at these things, and this is the plot on the left. And what you can see in the plot of the left is that people that have an age that is smaller than 25 years old were disproportionately denied the credit with respect to their neighbors, right? So you take this person who is less than 25 years old, and you look at the people who look the most similar to this person in terms of credit history, job, and other things that you're allowed to use to decide the credit, and you look at the people who were not that young, and but that are very similar, and you look at the difference in the proportions of people who got denied the credit in both groups, and in this case there is a big difference, or let's say a difference of, there is a difference of several percentage points between the two groups. On the right side you have, for instance, the opposite, right? Here the solid line in the right side represents males, and it shows you that actually if you're a man, and if it represents men that are married and are between 30 and 60. So it's kind of like a group that you will be, that is going to be favored by the algorithm, in this case, or by the decision. In this case, they show that the decisions are actually favoring this group. Now, this is enough to show discrimination, and here you can test for different attribute values. You look at these curves, and if you see a big separation, then you claim there is discrimination across this attribute value, and you can even claim now for that almost every individual that has this attribute value is being discriminated, and you can even exhibit a proof. And this proof is going to be these neighborhoods, right? So you can show the neighborhoods of the individual and place on it. Please. Good question. Thanks. Yeah, this is a great question. So the question is, you look only at the neighbors, you don't look at the radius. And actually, yes. So in their paper, they use KNearest Neighbors restricted to a certain distance, a maximum distance. So you're not allowed to you're not allowed to pick a neighbor that is too far from the distance, that is too different, because it kind of defeats the whole purpose of that you are comparing against someone who is equal. That's correct. So in this algorithm, the extended algorithm adds this requirement that the neighbors should be close enough to the original person. Thanks for the question. Now, you can use the same algorithm not only to discover that a certain attribute value is being discriminated against, but you can actually use it to kind of explain what are all these discriminations going on in the data, in the decisions, right? So how do you do it? It's very easy. You add a column. And you add a column for every individual. You do the computation for every individual in the data set, and you say, okay, is this individual, I do the neighborhoods around this individual restricted by a certain distance, compute the proportions, look at the difference of the proportion. If the difference of the proportion is larger than a certain amount, then I put a yes in the column. I say this person was discriminated, this other person was not discriminated, and so on. So you have a binary variable that says whether this individual was discriminated or not. So you have all the base attributes, the decision attribute, and now this extra attribute, which is whether you were discriminated or not. And now you do rule mining of this resulting data set, right? So you have augmented with an attribute, and now you look at all the attributes that explain this column. So for instance, in the German credit data set, we're going to take all the women who are female and married, or female, and you're going to look at all the cases where this woman was discriminated by more than 0.10, which means that the difference in proportions in terms of percentage points between the neighbors of her that were women in the same condition and men in the same condition is larger than 10 percentage points, right? And using the k equals 16 that we were using before. So for instance, here you look at you find some explanation, and you say actually the discriminated women had no children or not dependent, and we're asking for small loans. So you're going in a way, you're going deeper into kind of how this discrimination is expressed in these decisions, right? On the bottom you have you use a different classification rule mining method. It doesn't, for the purposes of the algorithm, it doesn't matter which method you use. And here you say, well, you have a more complex rule, and you say, well, the women who were discriminated were asking for small loans and were either paying in many installments or had been resident for a short time, right? So you now have, this is interesting of this KNN approach, because it gives you a sort of policy direction, right? It tells you not only that this group was discriminated by, but it goes deeper into what was the reason. And the method is very simple. You just add an extra column that tells if this individual was discriminated or not in terms of the neighborhoods of this individual. Now, KNN can also be used for discrimination prevention. This is going to be spoken at large in the second part of the tutorial after the break. We're going to speak much more about preventing discrimination, but let me kind of give you a small idea of how this discrimination prevention may work. You want to, if you want to create now a classification method, like a method for granting or denying this credit, and you want this classification method to be fair, you want both to have a high classification accuracy, and you also want to avoid the fraction of people who can claim that they were T discriminated, right? You may even want to reduce that set to 0, right? But you want to, at the very least, you want to have less rows in this output that have the discriminated column set to yes, right? So, and how can you do it? Well, you can take your training data, and in your training data you discover which people were discriminated against, and you flip the labels, and you say, well, I'm gonna create a different decision strategy that is gonna mimic the decisions that you have taken in the past, but we're not gonna make the same mistakes again. So for these people who were obviously and brutally discriminated against, we're gonna flip the label, and now they are gonna get the credit. And in the training data, and so my classifier will learn some indirect means to not discriminate against these people, and this actually works. Notice that it's not obvious that it should work, right? But it actually works, and so you have here the accuracy. This is accuracy in terms of reconstructing the same credit decisions. Of course. The bank will tell you, well, maybe these loans were for big amounts. I don't want to make mistakes in here or there, right? Of course, we're just measuring the decisions like as if every credit were equally important to the bank, and it's not the case, okay? You need to do this in a weighted way to avoid losing too much money, right? And then you have, but notice that, there is a very small drop in terms of accuracy, but actually the proportion of people that can claim that if they look at similar customers that didn't get the credit, the proportions were brutally different, like more than 10%, then the number of people has dropped dramatically in some cases, right? So depending on the method that you used for the method that you were using for classification before doing the pre-processing. And it's interesting because the pre-processing method is agnostic to this classifier, to the specific classifier that you're using. Okay, more. Bayesian networks. Now, let's go back to this method that was based on classification, right? So we saw the method on classification, we saw the method in KNearest Neighbors. Now we're going to come back for a moment to this method and look more closely at this extended lift, right? So remember, the extended lift was to what extent adding a protected attribute explains better the decisions than not having that extended attribute, right? Remember, there was something like how many females living in San Francisco didn't get the credit compared to how many people live in San Francisco, right? Or to what's the proportion of customers that were living in San Francisco, and what's the proportion of customers that were living in San Francisco were women. So now, if you look at this, these are confidences, right? And now we're going to shift a bit the idea and speak about probabilities instead of confidence. So let A be all the protected attributes. Let B be the context, like the unprotected attributes. And now, suppose we have a way of computing this probability of giving or not giving you the benefit based on some characteristics that you have, right? So we have this, suppose you have it, it's given to you. And now suppose you have it, you use it to classify people. So whenever this computation gives me something that is higher than a threshold, I'm not going to give you the scholarship, the credit, or the benefit. So if you can claim that the probability of being denied this benefit increases by more than alpha with respect to the probability when you add this attribute A, which was your gender, your race, or whatever, then we could say that this classifier is alpha discriminatory, right? We're going to augment, so this is the definition. We're basically extended the E-lift concept to a scenario where we don't have confidence of association rules, but we have probabilities. Okay? You can claim actually they are the same. Let's think of this as probabilities. We're going to add also these attributes R, which are attributes that we know from background knowledge that they are, or we know because we look at the data. These attributes R are going to be attributes that are so very strongly correlated with the gender attribute or with the race attribute and so on, right? So everything, these are going to be called redlining attributes, which they are attributes that you could use instead of the protected attributes, and they will have almost the same effect, okay? So A and R are the protected attributes, and B is the context, which is unprotected attributes, legal attributes, things that you can use, and that's fine. So now you can think of Bayesian network as just another method of computing, of generating like the decision, right? Or explaining the decision, right? So now in a Bayesian network, you're going to explain the decision in the end by tracing it back to several attribute values that influence each other and that eventually they influence the decision, right? So the Bayesian network is going to have several nodes, and those nodes are attribute values, and you are going to have one node which is going to be the decision, and you're going to have connections between these nodes that are going to be conditional probabilities, right? The probability of getting this decision, given that the person was female, given that the person had a certain race, and so on. And then you will have also these conditional probabilities between attributes, right? You will have what's the probability of not having a driver license if you are a female, and so on, right? So you have all these relationships between things. They are going to be encoded in this Bayesian network, described by this Bayesian network. So that's basically it. So now we're going to use the Bayesian network to compute the probabilities, and we're going to compare the probabilities when you have the protected attributes. So what are these probabilities when the probability of having a credit denied when you know that the person is a female or black or old or whatever, and we're going to compare them with the probability of having this outcome when you don't know these attributes, right? So the Bayesian E-lift or B-lift is basically the probability of C, which is the outcome, given all the attributes, divided by the probability of having this outcome, given only the legal attributes, the attributes that are context and you are allowed to use, and they are not strongly correlated with the protected attributes. They are completely safe, right? So we're going to look if this probability increases a lot, it means that the Bayesian network has found that it can explain the outcome very well by considering your attributes that you were not, that the data set is claiming that they are not using, right? So the decision is claiming that it's not being used. And okay, how do you use this for discrimination discovery? And I'm going to show you some examples a bit later on. How do you use this for discrimination discovery? Well, you build two networks. In the first one is just a vanilla Bayesian network. You take the data and you construct the data set has this code, which is the decision, whether the benefit was granted or denied, and you create this Bayesian network that has all these nodes, which are attribute values and probabilities. I'm going to show you an example. And this is the network. And now we're going to remove all the nodes that are protected attribute values. So we're going to remove the node age larger than 50, because for any legal ground, for legal reasons, we are not allowed to use it. So we're going to remove that node. And we're going to remove all the nodes that are connected to that node except for the class probability, right, for the outcome. So we're going to remove all those other nodes. And now we're going to use the two networks to compute the different probabilities, and we're going to apply this threshold. So if your new network computes the probability and there is a steep drop now, so first, two things must happen. First is that the network that uses the protected attribute and the network that doesn't use the protected attribute give you a different decision for a certain class, right?
And second, that this decision is now, the probability is now larger by a certain margin. So an example could be this. So you have the target variable here is how much do you have to pay every month. This is monthly premium on the top. So the target variable is how much will you be charged every month for your car insurance. And the other attributes are your gender, your occupation, the type of the car, and your history of accidents, right? And now, if in the original Bayesian network we uncover that your occupation depends on your gender, and that actually what you pay depends also on your gender, we're gonna just remove the gender attribute and remove the attributes that are connected to it, except for the outcome, which in this case is the monthly payment that you have to pay for the insurance. So you have this other network which is made only of safe attributes or legal attributes, right? And you can actually, and here what's basically going to be computed is the difference in the probabilities. Now, if you can also actually use the same method for trying to create a network that prevents discrimination, and it's very similar to the idea of KNN, that we saw in KNN. So you have the original network. Here the network on the left that includes the gender attribute that you're not supposed to be using for computing the monthly premium of the car insurance. And we're going to build a non-discriminatory network that is going to have the attribute node, the protected attribute node removed, the protected attribute value node removed, and we're going to keep all the redlining attributes, and we're going to correct the data set, the training data set, by flipping the class label of the discriminated instances. So if you find the people, basically find the people who were denied a credit or had to pay a high monthly payment because when the gender attribute was added, you look at those people, and now you flip the label and you say, we're going to suppose that didn't happen, and this person actually didn't have to pay the high monthly premium or didn't have the mortgage denied and so on. So we're going to flip the class label and retrain. And we're going to retrain the non-discriminatory network. And this will give us other probabilities and the outcome, and this is something they show on the paper. The outcome is going to be a network in which if you add or don't add this attribute, there is no big, the protected attribute, there is no big difference in the probabilities of, for instance, getting a high monthly premium and so on. Okay, so let me move on to some other approach that is based on probabilistic causation. And here I'm going to, for these other three approaches, I'm going to give you like really more like a high-level overview so that we can cover like more material. So notice that this probabilistic causation approach is based on it starts from some question that kind of may nag you, which is the fact that in all the other methods we have seen so far, we just show that there is some discriminatory outcome, but we don't show that there is, we show some correlations, but we don't show some causality. We show that the people who were denied a credit were overwhelmingly had like a certain ethnicity, but we don't show that this is in the correct causal direction, right? Yeah, ethnicity is not the good case, but whatever. So we don't show the causality. So the methods are correlation based, and of course, like the Bayesian network does not have a causal relation. So what this method is going to do is to augment this idea of Bayesian networks by using some restrictions on the causality. So let me show you how this is going to be done. So first, we're going to add two restrictions to this network. The first restriction is going to be that whatever we claim is causing something should come before in time, right? We cannot claim that something that age caused E if age happens after E. Okay, it's very obvious, right? So there has to be some temporal precedence, temporal priority. So you have causes before effects. And the second thing that should happen is that the effect should be increased. So the probability of having a certain effect given that you had a certain antecedent should be higher than the probability of not having that, right? In this case, remember that we are focusing on an outcome which is a negative outcome, right? So think of this like the probability of having the credit denied given that you had this attribute value or you didn't have this attribute value. So they have, in this paper, they present this causal network, this subspace causal network, which represents the structure similarly to Bayesian network, except that every arc in this network must satisfy these constraints, in both in terms of time and in terms of increasing the chances of the outcome, right? In this paper, they also sparsify a bit this network. So they remove some edges that don't explain much, and they keep like kind of the backbone of this network. They keep high probability. They pick high correlation edges and high causality edges in this case because the paper claims that you are also adding these extra attribute values. It's going to be much clearer with an example. So for instance, here you have the red attribute is a decision, and then you have, for instance, on the top right, you have the native country is India. On the top left, you have gender is male. Then on the center, you have old, and so on. So these are attribute value pairs, and the edges here represent like some inferred causal relationships between the different attribute values, right? So having a master education and so on, and so on. Now, suppose you are able to build from the data all these relationships that respect temporal precedence and that include an increase. They are all positive because they all represent increases in the probability of the target attribute value with respect to the origin attribute value. Of course, the thing about increasing is easy. The thing about temporal precedence is not so easy. In some cases, you have attribute values that have a temporal precedence. So, for instance, your education does not affect your age, right? Because your date of birth is predetermined before you actually get or don't get an education, right? In other cases, you can find other ways of relating these attributes in time if you have like a database in which you have time for these things. So, assume that for some data set, you actually have these temporal precedence relationships, and you are able to compute these edges in which one attribute value increases the chances of observing another attribute value, right? And this SBCN gives you a very powerful tool for analyzing discrimination as follows. So first, now you have a graph view of this thing. You may include both the attribute, the value of having like a negative decision and the node about having a positive decision, and you can use a simple graph partitioning algorithm to try to discover subgraphs, like dense subgraphs in this network. And in this case, for instance, if you look at like kind of the subgraph that includes the node with the negative outcome and the subgraph that includes the node with the positive outcome, you see some patterns which are kind of interesting because they reflect like some things such as, okay, you have among the people who didn't get the credit, you have widows, you have blacks, you have females, you have young, you have unmarried. You have many attributes that were discovered by other means to be discriminatory in this case. And in the case of the positive attributes, the reason why you get a credit, well, you have a husband, you have an executive or managerial position, you're a man, you're a certain age, and so on. Some of these may be discriminatory, may be protected attributes, some may not. What the simple graph partitioning on the network will uncover these communities. And the key idea that in this paper is used to find out whether some particular group having a certain attribute value is being discriminated is random walks. We're going to have these two nodes. One node is going to represent the positive outcome, for instance, having a high salary. The other node is going to be the negative outcome, having a low salary, and you have all these possible reasons for the decision. And what we're going to do is that we're going to start a random walk from a particular node. So I want to know if Hispanics get a lower salary than a higher salary, right? It matters to me. So I look at this node that says Hispanic, race equal Hispanic, and I do a random walk from that node following the weights of the edges, which are the strengths of these causal relationships between the attribute values. And I follow multiple times this, I do these multiple random walks, and now I look at the fraction of random walks in which I end up having a low salary if I start from the node that has a race equal Hispanic. And if that fraction, if this proportion is very high, then I can claim that this node having a race is a bad starting point, it's a bad attribute to have because it's going to impact your salary in a negative way, right? So whenever the fraction of random walks that end up in the bad node is large, I'm going to claim this is a bad node to start with, this is a bad attribute to have. And if that attribute is protected, then you're in trouble because it means that there is discrimination in this data set. Now, for instance, in the census income data set, if you look at things that have a very attribute values that if you start from them, you end up doing a random walk and you end up in a bad node, for instance, in this case, being denied the credit, you see that unmarried people are really in trouble in this. The left one is the census income. The left one is the target node. The positive is having a high income and the negative is having a low income. Sorry, on the left side, you have what are the reasons to have a low income, or what are these nodes that if you start from them, you will end up in a node that says you have low income, and you say, well, unmarried or never married or young or black or female are actually in the census data. All attribute values that can be traced forward to having a low income. And in the German credit, you have other attributes that can be traced forward to be grounds for being denied a credit. Now you can augment this network. You can use the same network to do other tricks. I'm going to show you two tricks that you can do. So one, if you have these occupational requirements that are legal, suppose having a driver license, they are encoded in some attribute values in the network. And if they are present, then this means that you can look at what is the fraction of random walks that lead you to the bad node, to having low salary or not having a credit, that can be traced back to these legal requirements. So whenever you're going to have this fraction of explainable discrimination, which is going to be the proportion between the walks that started from the Hispanic node and ended up having a low salary that goes through the node that had occupational requirement that was genuine. And in this case, for instance, you find that in the census income data set, you find that people who are of American or original American Indian origin, it's called not American Indian, it's called Aboriginal or Eskimo, that they end up having low income. You see that in many cases, these can be traced back to some intermediate state, which is not having a high school education, right? So in this case, you are giving something back. You're explaining that part of this discrimination against this group is because they don't have a high school diploma. Part of the discrimination that why female have a low salary is because they have an occupation which is in this category called other services, which is a category that for some reason it pays. It's a category of jobs that don't pay well. And this is the explanation of why. The same for young people. They end up in this category of jobs that don't pay well. And this explains part, in this case, you can even quantify some part of the low income. The other thing is that you can use this for individual and subgroup discrimination, which is very neat. Now suppose you want to know if black, female, young people are discriminated. Fine. You can do something that's called personalized Patron, which is like a simultaneous random walk from these three nodes, or it's a random walk with respect to these three nodes, and then you look at the result that you obtain if you start from these three nodes versus the result that you look at the proportion of random walks restarting to these three nodes that end up in the bad node versus the proportion of the total proportion of random walks that end up in the bad or the good node. And if the proportion of random walks that end up in the bad node is too high, then you can claim that this group that is characterized by having these attribute values is discriminated against, right? So you can, and it's good, it's an interesting trick because you can use it to make an arbitrary combination of attribute values and say something about the discrimination to that group. Okay, let me speak in the final two parts before going to the kind of wrapping up slides about privacy attacks. So the method for so the methods, remember that we said at the beginning that there is some relationship between discrimination and privacy. I'm going to unpack this relationship. So remember that the methods for discrimination discovery that we have seen require that in the data you have the protected attribute. In the methods we have seen the method based on mining the rules, the methods based on KNearest Neighbors, the Bayesian method, Bayesian Networks method. In all those cases, you need to know whether this row had or not was female or male, was black or Hispanic or whatever. You need to have the protected attribute. In some cases, you don't have it. In some cases, you have an aggregate that tells you, well, in this zip code, there are certain people, but you don't have the attribute value, right? In other cases, the data set might have even been pre-processed. Maybe the person who is giving you this data has pre-processed the data to hide, to show you, well, it's not that I didn't want to, I didn't use this attribute, I never had it, right? So they remove it from the data and they give you the data set, and now you're supposed to say something about discrimination or not discrimination in this data. So we're going to look at three scenarios here. One is discover that there is some indirect discrimination. The other is to do privacy-aware discrimination discovery, which means I don't even know whether you are black or white or female or male. I'm going to still discover that you were discriminated against. And then discrimination data recovery, which is some data that has been hidden from the authorities, right? You have some data that you have removed. And all of these things are very closely related to the idea of an attack in private data publishing, right? So I want to publish a data set, a census data set, an income data set, or whatever, and I'm going to make sure that people cannot reconstruct or reverse engineer my data to know who was whom. So I have this kind of scenario where I have an attacker that is trying to attack the privacy of my data set, and this is very similar. I'm trying to uncover the protected attributes from the decision. So we're going to see three attacks here. One is attack based on Frechet bounds, some attacks about inferring some attributes, and some other type of attack. So let's start with the first type of attack. Here we're going to just try to bound the discrimination in the data set, starting from the table that I showed at the beginning that has the decisions and the groups, right? So remember that this is alpha protective if the difference between the proportions is smaller than a certain number, right? And we're going to use this bound, which is a very kind of trivial bound. Right? The first part of this bound basically tells you that if you have two data sets, if you have two subsets and you have the intersection, then the intersection is smaller than each of the sets, right? It's a very obvious bound, right? The intersection is smaller than the two sets that make the intersection. It's very obvious. And then you have another bound related on the right, which is related to other properties of these subsets. So something interesting is that now suppose your input is these three tables. So it's the two tables on the right. So you don't know how many people in the protected group were denied the benefit, but you do know that people in certain groups that you know, for instance, people in a certain zip code, that is, in this case, think of a black neighborhood, were given or granted or denied the benefit, and then you know in this zip code how many people are black and how many people are white. So you have some indirect evidence. Again, so the table in the middle tells you the relationship between the groups and the outcomes, right? People in this zip code got the credit, people in this, not in this zip code got the credit or got the credit denied. And in the right table has background information. For this particular zip code, how many people belong to the protected group, how many people don't belong to the protected group. And the left table is unknown to you. You don't know actually how many people in the protected group were granted or denied the benefit. And what this technique does is that it bounds the numbers A and C. It bounds them using the information that you have about the groups and about whether the groups was protected or not protected and so on. So it gives you a way of kind of having a lower bound on the discrimination, right? And intuitively this makes sense. So if your data, if you don't have the outcomes, but you can show that you have, for instance, a zip code where only Hispanics live, and you notice that in this zip code everybody was denied the credit, then you can bound the discrimination against Hispanic in this way. So then another similar thing you can do with similar bounds is the following. Suppose we have this table. Suppose we don't know the religion of the people who applied for a job, but we do know that these people who was a bachelor or had a master's degree or a doctorate degree, a PhD, and had a certain job, didn't get the job or didn't get the job, but we know some groups. These groups may be, maybe we know the last name of the person. Maybe we know the zip code of the person. We know something. And we know for that something, we know, without having the identifiers, we know that there is a certain chance that you're a Muslim, a Christian, or a Jewish, right? Given your last name, given your zip code, and so on. And again, using the similar bounds, you can compute what is kind of a lower bound on the discrimination against this group, particularly in cases where the group belonging to a certain group is well correlated with having a certain attribute value, in this case with a certain religion, right? So on. And another thing you can do here is that you have a privacy attack. I'm going to skip it because I'm running out of time, but you have a privacy attack against this thing. Now, okay, in the 8 minutes I have left, let me show you some things related to one more method, and then try to wrap up this part. So this is just another way of thinking on the privacy attack, right? Which is this predictability approach. It's really just the same, stated in a different way. So you have your risk ratio now, which is the ratio between the people who were denied the benefit, so were in this case granted the benefit. The P1, this is wrong. It should be denied the benefit based on the group who were protected versus the people who were denied the benefit being in the unprotected group. And there is a note that this is kind of the likelihood ratio of the positive class. And this whole idea of disparate impact can be traced back to this idea of having a predictable attribute. So you have, this is as follows. So think of an adversarial situation. You have an algorithm that is run on protected and unprotected attributes, protected where all the race and so on. And Bob receives the data set with the outcomes. And now if Bob can predict the attributes, the protected attributes based on the unprotected and the outcomes, then the algorithm is discriminatory, and we know if the decisions are leaking information. And this is all explained in detail in this KDD 2015 paper called Certifying and Removing Disparate Impact, and it basically exploits this idea. So let me kind of wrap up with some 4 or 5 more slides. So there are many papers that have examined specific cases of discrimination using these tools. So for instance, you have this data set from Statistics Netherlands that classifies whether an individual is going to be dangerous or not, and is used by law enforcement agencies. And in this paper, they actually try some of these methods, and they discover that there is discrimination, and they actually show how you can change like the data to mitigate this. Actually, how can you create a different way of classifying people that have similar discriminating power between the people who are going to commit a crime and not, but does not discriminate against group, which is very interesting. And there is another case
that you can also look at, which is from 2013, where they use some of these techniques and they apply to some data set that has information about some grants that the Italian government was offering for research, and they actually show here that female researchers are discriminated against by the Italian government, and they show this using some of the tools that we have covered in this part of the tutorial. Interestingly, if you're interested in web data, you can use some of these methods for web data. There are many recent papers about discrimination in online services. So for instance, it says that if you're not black, you can charge like 12% more for your Airbnb apartment than if you're black. And this is shown by some researchers. There are many online retailers that do price steering that discriminate against a certain group. China is about 21% larger in Google Maps for China than in other Google Maps, and so on. Of course, this is all difficult. So it's difficult enough when you have all the data. On the web, you have all these problems of having to extract the data are noisy, it's difficult. You need to understand browsing behaviors, and it's more complicated, but in the end, you can apply the same tools and go on top of these technical difficulties and extract some consequences. So for instance, there are some very interesting cases like Latanya Sweeney, a researcher, she showed that if you search for a name such as Latanya, which is a predominantly black name, then Google will suggest you, do you want to look for criminal records for Latanya? Whether if you use a white sounding name, this doesn't happen so often. Some other researchers have studied Google Ads, and they show something really worrying, which is the following. You have two browsers, like two web browsers that have been, you start from zero with an empty cache, empty cookies, and so on. And now you start browsing the web and you follow you go to exactly the same pages and you do exactly the same. Then you go and create a profile in Google+. In one of the cases, you say you're a man. In the other profile, you say you're a woman. And now you go to Google and you search for jobs. And what happens is that Google will show you ads for jobs that pay less if you put in your profile that you're a woman, right? And this was discovered using this tool, which is called AdFisher, which is an automated tool that actually creates these browsers. It instruments a series of browsers. It creates the profiles for you. It does the navigation and everything. And it kind of tricks Google into believing that these two people differ in only one attribute, and then looks at the ads, do some significant testing, spawns more browsers if necessary, and so on. It's a very interesting tool to discover discrimination, and was used for this very interesting application that was determining that women were seeing ads for jobs that pay less than men. And that's all for my part. I think I have like 2 minutes for a question or questions. Okay.
So in the KNearest Neighbors problem that you mentioned the distance. So if you fix it radius r, are you going to pick like the top k? How would you, if there are more than k neighbors, how would you choose those?
Yeah.
What is the variance of?
Yeah. So the KNearest Neighbors will be the radius. What it does is that it includes in these groups. So notice that we're looking for the k-nearest, in this case female, the k-nearest female to this one and the k-nearest man. What it also does is that it restricts the search to a certain number. So you search for 4, maybe you only found 2, and that's it. Yes. Yes?
It's possible that, let's say you're building a credit approval model, and by all intention you do not want to discriminate, even by using directly objective variable or by proxy. But it's still possible that, to the extent that we have reflect society or whatever, some of the data mining will still turn out false positive. Is there any kind of counteracting statistics that maybe banks can protect themselves?
Yeah.
We can demonstrate that we really are not
Yes. So the question is whether, well, you are creating this predictive model and you have no intention to discriminate anyone, and you end up creating a model that actually has this discrimination. So this is the topic of the, it's a great question to wrap up the session, because that's the topic of the second part of the tutorial after the break. And it's about how to ensure that the classification building, like the learning, is done in a way that doesn't create a classifier that discriminates against a certain group. So this is one of where Francesco is going to talk about after the break. Okay, thank you very much. I see you at 10:30. Thanks.